Hello and welcome to Lecture 10 of our course on stochastic modeling of biological processes. In this lecture, we will discuss stochastic differential equations with multiple favorable states. An example is given as SDE 326 in the lecture notes, which we have already seen in our lectures 8 and 9. If K5 is equal to 0, then this stochastic differential equation becomes an ordinary differential equation, which has three steady states for our parameter values. We have chosen the coefficients K1, K2, K3 and K4 so that the two stable steady states are equal to 100 and 400, and the unstable steady state is just between them at 250. If K5 is not equal to 0, then we have observed in figure 3.1d that the solution of the SD326 fluctuates around the stable steady states 100 and 400 and occasionally switches between them. One of the most important characteristics of a stochastic system with multiple favorable states is the average time it takes to switch between two of those states. In this lecture, we will consider the SDE 326 as our illustrative example. Our main question is, what is the average time to switch between the favorable states of a stochastic system? There are many systems when such a question can be asked. In section 2.1, we discussed stochastic chemical systems with multiple favorable states, including gene regulatory networks and also a simple chemical switch illustrated in figure 2.2a. In this model, we plot the number of molecules of a chemical species as a function of time, and we observe switching between states with lower number of molecules and higher number of molecules. The parameters were chosen so that there are some quantitative similarities with the SDE326, with the lower favorable state being around 100 molecules and the higher favorable state being around 400 molecules. Another example of a system with two favorable states is presented in section 7.4. Here I have included figure 7.4b, where you can see a similar qualitative behavior, switching between two favorable states of variable ut. We will discuss this model in more detail in section 7.4. It is an example of stochastic modeling of collective animal behavior, and the plotted variable ut is the average velocity of a group of animals. While this is a completely different application area of stochastic modeling, there is switching between the favorable states of the system. Today, we will derive a formula for the average time to switch between favorable states of the SDE 326. An obvious question is, can we use a similar analysis to understand switching in other models? The answer is yes. Stochastic chemical systems will be discussed in our next lecture when we will cover section 3.8. The behavior of stochastic differential equation 326 was discussed in our previous two lectures. We have not only presented illustrative stochastic simulations in figure 3.1d, but also the stationary distribution in figure 3.2b, which we obtain both computationally and analytically using formula 339. To obtain a good estimate of the stationary distribution, we continued this blue trajectory for a much longer time than it is plotted in the figure on the left. This gray histogram was estimated using the simulation up to time t equal to 10 millions, that is 10 to power 7. Looking at this blue trajectory, we observe that the average time to switch between the steady states is about 100 time units. Therefore, we have estimated this gray histogram from a simulation which included around 100,000 switches between the favorable states and which was 10,000 times longer than the visualized trajectory on the left. The stationary distribution was obtained by solving the stationary Fokker-Planck equation. To further illustrate this separation of timescales, we can also study the time evolution of the probability density function. It satisfies the Fokker-Planck equation 331, which I have written here for our choice of coefficients f and g. To solve it, we need to specify an initial condition. Initial condition x0 equal to a given value corresponds to the initial condition for p given in terms of the Dirac delta function. In this video, I have chosen my initial condition to be uniformly distributed in a small interval around the unstable steady state 250. That is, we assume that our initial probability density function is the indicator function of interval 245-255. The time-dependent probability density function pxt is visualized as the red line, while the stationary distribution is plotted as the green line. Starting with this initial condition, you can see that the probability density function pxt converges to the stationary distribution, and the lines become indistinguishable within relatively short time interval of length 0,5. However, our initial condition is very special in a way that half of the initial distribution is closer to the lower stable steady state 100 and half of the initial distribution is closer to the upper steady state 400. So let us consider a different initial condition. In this video, my initial condition is uniformly distributed in a small interval around the stable steady state 100. That is, we assume that our initial probability density function is the indicator function of interval 95 to 105. Starting with this initial condition, I am visualizing here the same time interval, showing the time evolution of the probability density pxt from time 0 until time 0.5. We observe that the probability density function pxt seems to stabilize even quicker than in our previous case. All movement of the red line seems to stop around time 0.1. The resulting distribution has similar shape as the distribution around the lower steady state, but it has twice higher values, because there is no visible probability density around the second peak. This is to be expected, because we really only observe the system for a relatively short time interval. Remember that the average time to switch was of the order of 100 in our visualized time series. In figure 3.1d, as you can see here with the blue trajectory. In particular, a time interval of length 0.5 is very short comparing to the timescale on which switching can be observed. However, it is already long enough that the system reaches stationary distribution conditioned on being in one of the states. The mean switching time can be defined in different ways. Considering general non-symmetric systems, we could obtain different answers if we estimated the average time to go from the state 100 to the state 400 and the average time to go in the reverse direction from the state 400 to the state 100. In figure 3.3b, I calculated the average time to leave the interval minus infinity to unstable steady state xu, given that the simulation started with the initial value at point y. This quantity depends on y and is plotted here. The yellow histogram is estimated from stochastic simulations. For each value of y, I calculated the mean escape time from interval minus infinity xu as an average of 1000 realizations. That is, I initialized 1000 realizations of the SSA A6B6 at the same point x0 is equal y, calculated each realization until the simulation left the interval minus infinity xu, and recorded the times when the trajectory crossed the unstable steady state xu. Averaging over 1000 results, I obtained the yellow histogram, which is plotted together with the analytical result obtained in the lecture note as equation 363. We observe that the result is a constant for all initial conditions up to about 150. This is to be expected because it is in agreement with our observations made in the videos on the previous slide. If I start my simulation at any value y, which is less than 150, then the simulation quickly goes to the lower steady state 100 and then fluctuates around it. It takes about 0.1 time units to completely forget the initial condition, as we observed in the videos. This time is relatively negligible when we compare it with the time equal to 60, which is needed to reach the unstable steady state. When the simulation reaches the unstable steady state, there is a 50% chance that it continues to the other stable steady state and a 50% chance that it returns back to the lower steady state. Therefore, one possible way to define the mean switching time is to say that it is equal to twice the value to reach the unstable steady state. That is, we have to multiply 60 by 2 to obtain that the mean switching time is around 120. In the remainder of this video, we will discuss the derivation of formula 363. To derive formula 363, we will use the Kolmogorov backward equation derived in section 3.5. Considering the stochastic differential equation 3.6, we have previously derived the Fokker-Planck equation, which is also called the Kolmogorov forward equation in the literature. I have written it here in this form, where I use the diffusion coefficient defined as g square over 2. We have previously written the Fokker-Planck equation as an equation for probability density function pxt. In that formulation, we implicitly assume that the trajectory of the SDE36 started at a given initial condition at time 0. Thus we drop the initial time s and the initial condition y to simplify our notation. However, the Fokker-Planck equation is derived for this conditional probability density function, giving us the probability density at point x at time t, given that we started at point y at time s. Since p is a function of 4 variables, we can also derive a partial differential equation when we differentiate with respect of the initial time and initial condition. The resulting equation, called the Kolmogorov backward equation, is derived on page 75 of the lecture notes as equation 355. It is again a differentiated version of the Chapman-Kolmogorov equation, which can be written in the following form. Using the Taylor expansion of pxtzs around the point z is equal y, we obtain the Kolmogorov backward equation. You could again fill in the details of this calculation as an exercise. If you need more help, then step-by-step instructions are provided in the lecture notes on page 75. We can use the Kolmogorov backward equation to derive an equation for the average escape time tau y. To do that, we define the auxiliary quantity h, which gives us the probability that the trajectory did not escape the interval of interest during the time interval 0t, given that it started at y at time 0. Since we assume that our coefficients f and g do not explicitly depend on time t, we can shift the origin of time by t so these two integrals are equivalent. Integrating the Kolmogorov backward equation over x, we obtain the following PDE for our auxiliary function h. We are interested to calculate the average time to leave the interval minus infinity xu, given that we started at y. The time to leave this interval is a continuous random variable. Using the definition of the mean, its average, tau, can be calculated as an integral of t times the probability density function of this random variable, which is minus derivative of h. Using integration by parts, we conclude that tau is just an integral of h. In particular, we can integrate the partial differential equation 359 over y to derive the following ordinary differential equation for tau, which is our quantity of interest. Thus, we have obtained the second-order ordinary differential equation for tau. To solve it, we need two boundary conditions. If we start at the unstable steady state, then the time to escape the interval is 0, so our boundary condition at the right boundary is 0. On the other hand, if we start to the left of the stable steady state, then we quickly return to the lower stable steady state. So the function tau has to be approaching constant as tau goes to minus infinity. Thus, the second boundary condition is that the derivative of tau at minus infinity is 0. Integrating and using the first boundary condition, we obtain that the derivative of tau can be expressed in this form, which I have written in terms of the stationary distribution Ps. Integrating again and using the second boundary condition tau at xu is 0, we obtain the formula 363, which I have plotted in figure 33b as the blue line. It compares well with the results obtained by long-time stochastic simulations visualized as the yellow histogram. Both the theory and the simulations confirm that the average escape time from this interval is around 60. And this value does not seem to depend on the starting condition as long as it is less than about 150. Here I would like to note that we have never used in our derivation that xu is the unstable steady state. We only use it at the end, when we calculate the mean switching time as twice the value of the escape time, which is 2 times 60 equal to 120. In particular, this formula is valid for other intervals as well. If we define tau y as the average time to leave the interval minus infinity b for arbitrary b, we would obtain the same formula, where xu is replaced by b. And this formula is exact in a way that we would obtain a perfect match between the theory and the simulation, provided that we estimate the yellow histogram from very long time evolution of the system, and provided that we use a sufficiently small time step in our computer implementation. If we do not get a perfect match, then we can improve the comparison by increasing the length of the simulation and by decreasing the simulation time step. This brings me to the end of lecture 10, where we have continued in our discussion of chapter 3, covering sections 3.5 and 3.6 on the Kolmogorov backward equation and estimating mean switching times in systems with multiple favorable states. Please read pages 75 to 80 of the lecture notes before watching the video of lecture 11. In our next lecture, we will return back to stochastic chemical systems. Having developed a theory for estimating mean exit times and mean switching times in SDE models, we can further analyze stochastic chemical systems with similar behavior. Thank you very much for listening to Lecture 10 of our course on stochastic modeling of biological processes. Bye bye.